Hello! Today in our lesson we will learn how to write down the nuclear equations of reactions that accompany the two processes alpha decay and beta decay. We'll analyze these tasks with you using 4 examples. So what you need to know in order to be able to do these assignments, first of all, you need to know the characteristics of these radiations themselves. Alpha radiation, beta radiation, and one remark. Notice that the neutron particle, which is found in the nucleus of every chemical element, can decay to form both a proton and an electron. And this is the basis in particular of the nuclear process, which accompanies decay. So let's have the first element that we're going to look at alpha decay for, if it's the element polonium, with a number and a mass. So it turns out that there is alpha decay, and therefore we've got helium splitting off, and the element that we're going to get will have a sequence number and an atomic mass. And so we need to establish what this resulting element will be. So first write down a schematic of the process where the unknown resulting daughter element that is produced by the decay is a question. So what do we first have to do? We have to determine the mass and the charge that we get in this case for our particle, which is labeled in this hidden way. So, well, let's see. The first thing we have to consider is that we have the number in on top. I draw your attention, according to the Sodifean's rule, we must also have on the right side of the sum. That is, 4 is the mass that has the helium particles, and then plus what our unknown element, let's call it A. And then this mass, according to the calculations, we have. Now we do the same manipulation with respect to the number. And then we have helium, we have 2. And plus we have the number that our unknown element has. Then this Z, in this case, we will have 82. Then we have to identify which element, but since the main characteristic is the sequence number, we can say Z equals 82. Therefore, it's lead, and lead will have its ordinal number or its atomic number, and here is what we established here earlier. Well, now finally we write down our resulting equation. So, polonium at alpha decay with the splitting off of the nuclei of this particle, we got the unknown element. Now it is clear to us, lead, it's number 82. Now we figured out which element was the unknown element in this case. Now we move on to sodium, and for sodium, let's deal with its beta decay. Beta in this case minus. Then recall that our beta minus is electron minus 1, 0, and again, the unknown is the element we've got, which we have to decode. And look, we're going to proceed in exactly the same way. Here we have 24 is the number on top for sodium, and on the right side we have 0, and then A from here is also 24. Now looking at the bottom, we've got atomic number 11, and that's minus 1 plus Z. And then in this case, Z we must have, given the rules of math, must be 12. So since Z is 12, we conclude that this element is the element magnesium. number 12 and mass 24. And then we can write our equation with a specific child element. 11. 24 with beta decay -1 and 0 for the electron, and we've got magnesium 1224. Okay, let's do one for a more complex element, uranium. Now, uranium is alpha decay, so it's splitting helium. 2, 4, and then there's the unknown element that it has to go to. Z, and here's A. Look, we're working exactly the same way. On top of that, we've got 235. Then here we have 4 units, and here we have A. And this A from here is 231. Now at the bottom we have 92, in which case we've got 2 units at the bottom, plus Z. And Z, then we have 90. So now we have to identify some elements. Since Z is equal to 90, then the element we have with this number is the element Tyrrheus, which will have 90 with 231 on top. Well, let's write down the equation of the reaction. Uranium, 92, 235. So it's splitting off the alpha particle helium in this case. 2, 4, and in this case, the unknown element we've identified is thorium. 90 and 231. And the last example for lithium, it undergoes beta decay. In this case, beta decay is electron. Beta minus. And again, the unknown is the element we want to determine. So we do exactly the same thing. At the top we have 9, here we have 0. Plus A, so A equals 9. On the bottom we have 3, and since the electron is -1, plus Z, so Z would be 4, given the rules of math. So since we have the number 4, it's easy to conclude that the element in question is beryllium. 4 and its mass is 9, and we'll write down the equation that we've got. So lithium 39, when beta decays -1 and 0, and it goes into beryllium, 4 and 9. This is how our nuclear reactions are written down. As you can see, these calculations are not very complicated, and it is important to correctly calculate the sequence number, and it is, pay attention, the most important value. But the mass, it is a secondary characteristic. So when you identify an element, pay attention. The key in each case is the atomic number, because the mass of isotopes can be different, so you cannot check the mass of an element. It is the atomic number that is important, which allows you to find that element in the periodic table. So today we looked at how decay, alpha and beta decay happen. In the next lesson, we will talk about how the emission of these same particles occurs, that is, bombardment by such particles, and we will proceed in exactly the same way, calculating and drawing conclusions about what kind of elements will eventually be recorded in our nuclear reactions. Goodbye.